This is a microchip. When you zoom in, you find a nanoscopic computing city. Skyscrapers hundreds of layers tall with hundreds of kilometers of wires connecting everything. And at the very bottom is this: transistors. Billions of them. They are the ones and zeros of our computer. The chip works by whizzing electrons from transistor to transistor. And the smaller you can make those transistors, the less the signals have to travel, so the faster they can compute.
Plus, you can fit more transistors into the same area, resulting in a much more powerful chip.
So for over 50 years, transistors got smaller and smaller, and the number you could fit on a chip doubled every 2 years. This became known as Moore's Law, named for Intel's co-founder Gordon Moore after he noticed the pattern back in 1965, and it's been one of the main drivers of the tech industry. But around 2015, progress came to a screeching halt.
And we might have never gotten past it if it wasn't for a single company
that makes these machines, the machines that saved Moore's Law.
Holy! This is a video about the most complicated commercial product humanity's ever built.
That's insane!
For 30 years, almost everyone thought that actually building this machine was impossible. And yet, it exists. There is only one company in the world that can make it. So what is this company? And what is this impossible machine they've built?
To make a microchip, you start by taking silicon dioxide, usually from sand, and purifying it into ultra-pure, nearly 100% silicon chunks, which is then melted down in a special furnace. Next, you lower a small seed crystal into the vat. Silicon atoms attach to the crystal, extending its structure. Then you slowly raise the seed crystal while rotating it, and this results in a large single crystal silicon ingot. The ingot is then cut into wafers with diamond wire saws, up to 5,000 of them, after which each wafer is carefully polished. Next, it's coated with a light-sensitive material called photoresist. Then you rinse the wafer with a basic solution to wash away the exposed photoresist, leaving the design imprinted. So now you can actually turn this pattern into physical structures. This is often done by etching into the uncovered silicon by using either chemicals or plasma. And then you deposit a metal like copper to fill in those etched lines. As a last step, you wash away the remaining photoresist, and now you've made a single layer of the chip. We've simplified this cycle down to the main steps: coat, expose, etch, and deposit. It repeats for every single chip layer, and depending on the chip, there could be anywhere from 10 to 100 layers. The bottom layer is the transistors. This is the most complicated layer, requiring hundreds of steps that all need to be perfect. The higher layers are a little easier. These are the metal wires that carry signals and power. By the end, the completed wafer can have hundreds of chips, which are then cut into separate pieces, packaged, and put into products.
But by far the hardest and most crucial step in the process is where you shine light through the mask and onto the wafer. This is photolithography. And that's because this step determines how small you can make the features.
Since there's a limit to how much you can increase the numerical aperture, to 1, over time the only way to keep making smaller and smaller features is by using shorter and shorter wavelengths. So this is exactly what happened up until the late 1990s, when the industry settled on 193 nanometer deep UV light. This was the light that was used to make all of the most advanced chips right until around 2015. But by that point, scientists had reached the limit to how small they could make the features, and Moore's Law was about to run into a brick wall. So a radical change was needed. Over the past 30 years, the US government had invested billions of dollars into national labs to maintain the country's technological edge during the Cold War. But by the late 1980s, the Cold War was slowing down, and all these labs were sitting on research that had commercial potential. So the government encouraged the labs to partner with US companies to turn that research into products and to stimulate the economy. And the government would then supply seed money. They even gave the technology a new name: extreme ultraviolet lithography, or just EUV.
But then in 1996, the US government cut funding for the project. This spelled disaster for the big chip companies like Intel. The industry estimated that the 193 nanometer lithography tools would fall behind Moore's Law by 2005. But there were no other alternatives.
So Intel, Motorola, AMD, and other companies got together and invested $250 million to keep it going, making it the largest investment ever by private industry in a Department of Energy research project. By the year 2000, the labs had produced this, the Engineering Test Stand. It was the first fully functioning EUV prototype. It produced 9.8 watts of 13.4 nanometer EUV light, which was then reflected by 8 mirrors from the source to the mask to the wafer. It could print 70 nanometer features, and it proved that EUV could work.
But the prototype had a major flaw. It could only print about 10 wafers per hour. And to make EUV economically viable, it would have to print hundreds of wafers per hour, 24/7, 365 days a year. The main reason output was so slow was because the light reflected off of 8 mirrors and the reticle, which is also a mirror, just with the design imprinted. Traditional masks that allow light to pass through don't work because, well, they absorb all the light. And so, one by one, American companies walked away from developing a full EUV lithography machine. That left just one company, ASML. They would work together with their German partner Zeiss, where Zeiss would take care of the mirrors and ASML would focus on the light source. To make the mirrors, Zeiss used a process called sputtering. A target of coating material is bombarded with either plasma or ions, causing atoms to be ejected, fly off, and stick to the mirror. This is a messy process, so the layers end up having bumps and gaps. With the mirror design locked in, ASML needed a source for that specific wavelength. This method uses a high-powered laser to hit a target material, creating a plasma that's more than 220,000 degrees Celsius hot. The electrons have so much energy that the nucleus can't hold on to them anymore, and up to 14 electrons escape their orbits. After the laser shuts off, the electrons and ions recombine to produce light. This is laser-produced plasma, and it was the only method that seemed scalable. But xenon had a big problem. The conversion efficiency, that is the ratio of usable light to the amount of power you put in, was terrible. It was only around 0.5%. That's because while xenon does emit light in the 13 to 14 nanometer range, there's much more light released around 11 nanometers, so most of the energy went into making light that the mirrors couldn't reflect. Plus, the laser didn't ionize all the atoms, so leftover neutral xenon atoms would strongly reabsorb some of that 13.4 nanometer light. Now, tin has a much higher emission peak, around 13.5 nanometers, which results in a 5 to 10 times higher conversion efficiency than xenon. But just like xenon, neutral tin atoms also absorb EUV light. So they came up with a crazy idea: to shoot one tiny tin droplet at a time. But to get the required power, you would have to make and hit thousands of droplets every second. To make the droplets, extremely pure tin is melted and pushed through a microscopic nozzle by high-pressure nitrogen. This nozzle vibrates at a high frequency, breaking the stream into tiny droplets. These droplets are irregular in size, shape, velocity, and distance, and the whole process is chaotic.
That's like our magic sauce, is how do you modulate that tin jet so that it forms the droplets we want and that they're stable.
I think we found some paper that described this process, and it was sort of eye-opening to me that it seems like all the droplets actually come out irregular out of the nozzle. But then before they reach the side where they get hit by the laser, like the little irregular droplets come together to form these perfectly spaced, perfectly regular droplets that are about the same size and shape and all traveling at the same velocity. That feels like magic to me, Jason.
Yeah, it's exactly that. It's how do you take a long stream of a tin jet that wants to break up into all these irregular droplets and like force onto it that it's going to collapse into a single droplet and then happen again and again and again.
But these droplets not only have to be identical, they have to be moving incredibly fast.
What will happen is if the next droplet that's coming down the line is too close, then it'll actually get like disturbed and mess up the next plasma event. So we have a requirement, which is both that we make 50,000 droplets per second, but also that they're traveling extremely fast.
By 2011, their laser-produced plasma source reached 11 watts, which was more than double what they managed with their previous source. But they were still limited to just 5 wafers per hour. So they needed to increase the power, and fast, because they promised they'd hit 60 wafers per hour by the end of 2011. Unfortunately, this new method had a major flaw.
Now the problem with the tin is you hit the droplet, you generate EUV with a very decent conversion efficiency. Where does the tin go? Because like, 30 centimeters away, you have this atomically flat, very beautiful, very expensive mirror from our friends at Zeiss.
Yeah.
And in the early days, we would coat the thing within like this.
These machines need to run for a year. You're putting liters of tin through this plasma event, and a single nanometer of tin, if it was to land on that collector mirror, you'd have to take the collector out of commission. We need to keep it almost perfectly clean for a year.
Yeah, how do you even approach that?
So our main tool here is the hydrogen gas, actually.
They filled the chamber with low-pressure hydrogen. This slows and cools the tin particles down. And even if some tin makes it to the collector, the hydrogen pulls it off to form a gas called stenane. This way, the machine cleans the collectors while it's running. But that hydrogen gas also gets hot from all those tin explosions. So they need to keep flushing new, cooler hydrogen into the system while flushing out the stenane and hotter gas. But they had to get the pressure and the flow rate just right. I mean, too little hydrogen and the mirrors would get too dirty, but too much hydrogen would not only absorb too much EUV light, but it would also cause the system to overheat. 2012 came and went, and they still didn't have enough power. In fact, by 2013, ASML just reached 50 watts by shooting 50,000 tin droplets per second. But this increased power came at a price, because more power means more heat that ends up slightly shifting the mirrors, resulting in misaligned light and misaligned chip layers. So Zeiss built a nervous system directly into the optics, robot-guided sensors that constantly measure the exact position and angle of each mirror, down to the nanometer and the pico-radian, which is absolutely insane. While Zeiss was doing a stellar job with the optics, ASML was still struggling with the power source. The problem was that the tin droplets were too dense, meaning that most of the emitted EUV light was still getting reabsorbed by the neutral atoms before it could ever reach the collector mirror.
The way we blasted the droplet was so not enough light, too much debris.
To make matters worse, they could see that about 10 years from now, they would need a new generation of machine, a high-NA EUV machine. Essentially one with a larger optic system that could print smaller features. So what did they do? They decided to double down and invest in the next generation before they even got the current one to work. Not only are you all in on EUV, you're doubling down even before you know if EUV is going to work.
Yes.
But to keep funding the development, they needed money, and lots of it. So they turned to the very people who needed this technology.
ASML reached out to its main customers. Okay, you want this technology for the next generation of chips? Well, you need to make us able to invest more by investing in us.
Intel invested around $4.1 billion, and Samsung and TSMC invested another $1.3 billion combined. So they can keep the research going, but with no product to show, customers were running out of patience.
We were crucified at every conference that the promises we made last year we were unable to live up to.
Yeah.
And they said, this is what you showed 2 years ago, this is what you showed last year, this is what you're telling me this year, so why would I believe you?
They were getting desperate.
But this was, I think, about 2012 or 13. We were struggling to get the EUV power up.
The big idea was, instead of hitting the droplet once, hit it twice.
One shot to hit the droplet and it expands in like a pancake shape.
Yeah.
And then, only then have the second shot, the more powerful main pulse, where you evaporate the pancake and turn it into a plasma. Yeah. This was a major breakthrough.
By changing the target from a droplet to a pancake, you got a larger surface area for the laser to vaporize, but without the cost of adding more debris or neutral atoms, because now the tin is vaporized all at once. By 2014, they finally managed to hit that coveted 100 watts mark. But improvements in multi-patterning with 193 nanometers now meant that EUV would only be useful if the source reached at least 200 watts and made 125 wafers per hour.
As the industry moved on, nobody waits for you. You know, they find other solutions. We had to catch up.
One of the problems was, how do you perfectly time the laser so you hit each of these droplets?
So the analogy is a bit like a golf ball that you need to land in the hole 200 meters away. Not like land on the green, not bounce and then get in the hole, but like land in the hole every time. That's the level of precision that we need to deliver the droplets. Those droplets are traveling through this like maelstrom of hydrogen flow. The speeds are tremendously high. It's like shoot golf balls through a tornado. And then right when it lands at the hole, that's when it needs to get hit by the laser. So in order to basically track the droplets, for that we use laser curtains. And we can sort of look at when does the droplet pass through a laser curtain. Those scattered photons tell us basically when and where is the droplet. And then importantly tells us when to fire the laser. So we actually have to take into account how long will it take for the light pulse to hit the droplet after we send the pulse.
Now, by 2015, they were getting closer and closer to that coveted 200 watt mark. With the source power up, there was one final problem that had to be solved before they could begin manufacturing their machine. See, while the hydrogen gas did protect the collector mirror from debris, it wasn't perfect. All the intense high-energy photons and hydrogen ions zipping around deteriorated a very special top coating on the collector. So they still had to clean the mirrors every 10 hours, which, is terrible for productivity. Then one of the engineers noticed that every time they opened up the machine, the mirrors suddenly seemed cleaner.
Whenever we open up the machine, oxygen comes in and our problem is solved. Couldn't we think of a way to add just a little oxygen to our system? We'll keep the collector clean for longer.
With this fix, ASML's machine could run continuously for much longer, and it finally became commercially viable. By 2016, orders started pouring in, and now all of the most advanced chips need ASML's machine, making them perhaps the most important tech company in the world.